Hello, we will explain gamma distribution in this video. Gamma distribution is a distribution to model random variable. So it is to model the time until next several events occur. So the probability density function of gamma distribution can be expressed as this formula. And we have two parameters, alpha and lambda. So alpha is called shape parameter. Lambda is called rate. So rate means how often the next event will come, or next several events will come. And alpha model one or several this number. So for example, if we want to know what's the time, average time until next event, so here alpha is 1. And actually this gamma distribution will reduce to exponential distribution. So exponential distribution is the special case of gamma distribution when alpha is 1. So here generally gamma distribution will include a gamma function in the denominator, and in the numerator is e minus lambda x, then lambda x alpha minus 1 in the power. So here x is what we have said called time. So until the next event, what's the time until next several events? And the gamma function can be calculated with an integral from 0 to the positive infinity, and also include the lambda x alpha minus 1 in the power, then e minus lambda x in the power, then times lambda and integral over dx. And its result is like this one if we use y equals lambda x. So sometimes another type of expressed gamma function is like this one. So here we can use, for example, x. So e minus x, then x alpha minus 1 dx. So these two is the same if we just take x is lambda x, right? And calculate gamma function, we'll use integral like u dv integral equals uv minus v du integral. Then it will reduce to like this one. So if we calculate the gamma alpha, because this is gamma alpha, right? Then the result will be alpha minus 1 times this expression. But if we look at this expression, it actually is gamma alpha 1, alpha minus 1, right? So it's very interesting. Gamma function, so gamma alpha times equals alpha minus 1 times gamma alpha minus 1. Then it will iterate it until gamma 1. So gamma n, so here n is same as alpha, right? So we can write gamma n equals n minus 1 factorial, then times gamma 1. And the gamma 1 is 1, right? So it's very interesting. And if we want to know in detail of gamma distribution, we have to use moment generating function. So moment generating function is expectation of e tx in the power. So here t is a scalar variable and tx is the random variable. Then we can get phi t is lambda divided by lambda t in numerator, then alpha in the power. So this is expression of gamma distribution, gamma random variable moment generating function with the parameters alpha and lambda. So next, then we can take derivative of moment generating function with respect to t, get these results, and we take a second times derivative with t, we'll get this result. Then we take the value of t is 0, for both 1, then we'll get expectation of x actually is the first derivative at t is 0. And the variance of x is the second degrees derivative taking value t is 0 minus the expectation's power. So we get the variance is lambda square in the denominator times alpha, and expectation of gamma distribution is lambda in the denominator then times alpha. So actually this is a very interesting result. Then you can also see if the parameter of a gamma distribution is x plus x1 plus x2, then the result will be alpha 1 plus alpha 2. If x and x2 are two gamma independent gamma random variable with alpha 1 lambda and alpha 2 lambda. So actually their moment generating function is the same scalars power with different power. Its power is just alpha 1 plus alpha 2. So this is also very interesting. From this result, we can get some further corollary. If xi, I is 1 to n, are independent gamma random variables with respective parameters alpha, I, and lambda. So these independent gamma random variables have the same lambda but different alpha I. Then the summation of these random variable is also gamma random variable, and with the parameter sigma alpha I, then with the same rate. So their shape will be summed together if we will model this random variable, which is the summation of n independent random variable from gamma distribution. And because when alpha is 1, the gamma distribution reduced to exponential random variable with raised lambda. So we have also this result, which if xi to xn are all independent exponential random variables, though their summation follows a gamma random variable with a parameter n lambda. So here n is the same as the alpha, which is the summation of 1, 1, 1, 1, right? So we say n here. So the example from this theory is that if the lifetime of a battery is exponentially distributed with rate lambda, so if a stereo cassette requires one battery to operate, then the total playing time one can obtain from a total of n batteries is a gamma random variable with parameter n lambda. Why? Because the cassette requires only one battery. So which means one battery lifetime ended, then we take another battery to use, and so on, until n battery is all used out, right? So the lifetime actually is lifetime of this n battery. Because one battery follows exponential distribution with a rate lambda. So summation of this n random variable will follow parameter n lambda, right? Because each has alpha 1. So their summation will follow a gamma distribution with the summation of alpha. So summation of alpha actually is summation of n1, which is n here, right? So the total playing time for this stereo cassette has follows a gamma distribution. Their lifetime follows gamma distribution with a parameter n lambda. Thanks for watching.